program, but also we have a very active program for visitors. In case you want to visit, besides the workshop or whatever, just let us know and we'll be happy to host you and have your hour. So without any further ado, let me just inaugurate the meeting, and let's start with Timo Weigand, the blackboard of before that. Sorry, the first one is that the linear combination of this room and depending on whether the talk is blackboard or not, will be located here or there. Okay, so we'll be instructing you where will be the next meeting for. For the moment we are here. After the break, I think we go to the other room, which is right in the middle near the registration. The second announcement is that there is a small change in the program, and the last speaker of the morning session will be Fabian Duel instead of Thomas Kuhn. Okay, so the last change that we will have. So thanks a lot, and it's Timo, thanks for coming, and we are looking forward to it.
Thank you very much. Thank you very much for the invitation, and thanks a lot to the organizers for putting together the workshop here. It's always great to be in Madrid. So in the talk, I'd like to discuss various aspects of, it's good to take one train early, of matter in F-theory. As we know, in order to understand matter, in particular charged matter in F-theory compactifications, we have to address at least two aspects. First, we have to understand the structure of the two singularities and their resolution in elliptic fibrations. So that's purely geometric. And so we have to understand, at least in Calabi-Yau fourfolds, so compactifications to 4 dimensions, into 2 dimensions, the gauge backgrounds in order to properly do the zero-mode counting. So I hope it's appropriate to combine these aspects because both of them are related to our attempt to understand matter in F-theory compactifications in one. In particular, in the first part, I'd like to discuss certain specialities in codimension 2 singularities of elliptic fibrations, namely complications due to unresolvable singularities. I'll discuss what this is to mean, and I'll be focusing here on Calabi-Yau threefolds. Then, in the second part of the talk, I'll discuss the second aspect, namely the matter multiplicities and I will here be discussing the smooth case of Calabi-Yau fourfolds, and in fact, this is also applicable to Calabi-Yau fivefolds. So ideally, I'd like to combine them and be able to be doing the second part. So in situations with singularities, this will be able to work. Okay. So let's start. F on elliptic Calabi-Yau folds with singularities. And before we come to the gist, I'd like to introduce a few mathematical definitions that are probably known to all of us, but just so that we have everything collected. So we'll be mostly interested in so-called Q factorial, we'll discuss it, terminal, singularities, on threefolds. And since they will be featuring a lot, we will abbreviate them as QFTs. Terminal singularities. Let's consider X a complex algebraic threefold. We will allow it to be singular singularities. But the singularities are such that the threefold will still be what's known as Gorenstein. Gorenstein means that the canonical bundle is a line bundle, or the canonical divisor, K, is a Cartier divisor. So the canonical bundle is really a line bundle, not just a sheaf. Since X is singular, we study its desingularization or its resolution, as we are very used to in F-theory, of course. We consider a resolution. This is a birational map from X to X tilde, or from X tilde to X, where X tilde is smooth. And X tilde and the inverse image of X agree, except on the exceptional set. So the exceptional set is where these two differ. And depending on how big this exceptional set is, one distinguishes between big and small resolution. F, the resolution is called small if it is an isomorphism in codimension 1. So if the two start differing in codimension 2 and higher, then it's called a small resolution, and otherwise it's called big, if it is not an isomorphism in codimension 1. So if the exceptional set includes divisors, so codimension 1 loci. Then if one considers such a resolution, it's important to compare how the canonical bundle, which is a line bundle by assumption, differs for x tilde and x. So the canonical bundle of x tilde is given by pulling back the canonical bundle of x, but then there is a discrepancy here. This is written as in terms of the AI, EI, where the EI are exceptional divisors, if they exist, so if we have a big resolution, and the AI are called the discrepancies. Which tell us how different the two spaces are. And now comes the key definition. If for A, or equivalently for any big resolution, all the AI here are positive, strictly positive, the singularity is called terminal. Then X has, at worst, terminal singularities. And if the AI are bigger than or equal to 0, X has, at worst, canonical singularities. And then one can go on in the definition, KLT and log terminal if they are bigger or equal to -1, but this is what we will need. If kx tilde and kx do not differ at all, then the resolution is called crescent. If kx tilde equals kx, the resolution is crescent. So in particular, if we start with, say, a Calabi-Yau and we have a crescent resolution, its resolution is also Calabi-Yau, of course. So why are those two types of singularities of relevance? The relevance is canonical singularities can be reached at finite distance in complex moduli space, starting with a smooth Calabi-Yau, or with a smooth space. Once one has a canonical singularity, one can do a partial resolution, crescent, without changing kx tilde, such that at the end of the day one is left only with terminal singularities. So the terminal singularities are what you get after a partial crescent resolution of the canonical ones, which are the ones that you get at finite distance in moduli space. That's why they are important. They have two important properties, namely terminal singularities on a threefold, that's also crucial, are isolated. That is unfortunately, I think, not true anymore in Calabi-Yau fourfolds. They are isolated, and they are analytic hypersurface singularities. So one can write them locally as an analytic hypersurface equation, which is singular. So one has them relatively well under control. Okay, so if we have a terminal singularity and we do a big resolution, then the canonical bundle will definitely change. However, if we have a terminal singularity and we do a small resolution, then by definition, since the divisors here are not there, the canonical bundle does not change. So the question is, when does a small resolution exist, because it's crescent? And the criterion is Q factoriality. This is why we need the second specification. So the Calabi-Yau is called Q factorial if every while divisor, so every codimension 1 cycle, is Q Cartier. So if every while divisor, the while, there exists some integer m in Z such that m times it is a Cartier divisor. So this means that one can find a covering of the whole space such that this divisor is given by the vanishing of one equation in each open set. And when this happens, then we cannot have a small resolution. That is the crucial point, the crucial fact for this talk. A small and hence crepant resolution of a terminal singularity, and it in fact holds more general, exists if and only if x is not q factorial. So put differently, if we have a terminal singularity and the space is q factorial, so every while divisor is Cartier divisor, then no crepant small resolution of the terminal singularity exists. Only a big resolution exists, but it necessarily changes the canonical bundle. And a key example for this would be the non-resolvable conifold. A conifold is terminal, so we can always do a big resolution, but it always is terminal according to this definition here. We can do a small resolution if it is not q factorial, then we can just blow up. But this might be obstructed globally. So again, if x, this is, let me make the reverse statement, the same statement. If x has q factorial terminal singularities, QFTs, then no crepant resolution exists. Okay, so that's the definition. Questions on the definition so far? Yes? Yes? Well, yeah. Yes, if it's canonical but not terminal. If kx tilde is kx, I would call it crepant. If all the AI are 0, this is in particular canonical. Canonical and not terminal. No. It's an orbifold singularity. Yeah. Yeah. Hmm? Yes. Yes. That doesn't matter. If it's terminal, then it's a hypersurface singularity. Okay, I should say terminal, but not canonical. Sorry, yes. Terminal but not canonical. Sorry, good point. Okay, so what's the relevance, what's the context now after this definition? So relevance for us in F theory, and then in matter. We'll come to this, of course. Relevance for elliptic Calabi-Yau threefolds. So by Calabi-Yau threefold, I mean an object, so a threefold, such that kx is trivial, Gorenstein, and kx is trivial canonical bundle, and h1, 0, h2, 0 vanishes. So we are all used to writing down Weierstrass models over a base now b2, y squared equals x cubed plus fx z4 plus g z to the 6th. This would be a elliptic vibration over a base b2. Calabi-Yau. I choose it such that it's Calabi-Yau. Then the famous statement is that as long as the vanishing orders of f and g are not too bad in codimension 1, so don't exceed 4-6 bound, then up to possibly blowing up the base, one can always find a partial, flat, and decrepant resolution of the singularities, except that one might end up with such Q factorial terminal singularities in codimension 2. So that's why all this nonsense is important for us. So as long as the order of F and G do not exceed the 4/6 bound, sloppily written like this, in codimension 1 on B2, then there exists a flat, so equidimensional resolution, so the fiber is always a dimensional one, crepant, so the resolution is still Calabi-Yau, partial, so not all singularities are resolved. Possibly, I have to, up to blow-ups of the base, so birational changes of the base, so I might have to blow up devices on the base. But the point is, up to the appearance of, in the partial resolution, Q factorial terminal singularities. So these might still be there, and they necessarily appear in codimension 2 on the base, so at points. These are isolated singularities. And that's why it's easier to deal with Calabi-Yau 3 first, because there they are really isolated point-like singularities, which will become more complicated than on higher. So these guys can appear, and the question is, are they just exotic or do they appear often? And the statement is they appear often. So if we build an arbitrary model, then it might very well occur that we run into those complications. Yes? I think so. I think it is finite number. Yes, that's Antonella Grassi's theorem. Yes. Thank you. So such QFTs in our situation occur often. So they are not just side effect. So for example, consider a Weierstrass model. Consider the most generic Weierstrass model with the following property. Such that the discriminant, so that i.e. the 7-brane locus, takes the following form, is factorized into 2 pieces. So we have our base, B2, and our discriminant factors into 2 pieces, a piece sigma 1 and a second piece sigma 0, where over sigma 0, I1 Lyra type, so smooth singular fiber but no singularity, and over sigma 1, an arbitrary gauge group, including triple 1. But we take the most general situation where the discriminant factors into 2 pieces. There are 23 different families of that type that one can write down. So writing down all possibilities, not going up to above 4/6 in codimension 1, including infinite families such that where you here have an SUN group or an SPK group, etc. These were studied by Grassi and Morrison systematically, among others. So there exist 20 families. Yes, these are classified. These are classified. Just the Weierstrass models now, over a generic base. I take the base, say P2, generic base. Tunable, these are the tunable models over generic. So 23 families of such model. Grassi and Morrison looked at them in detail in 2000, I think, and then 2011. And the point is, 3 of them have this property of Q factorial terminal singularity. 3 have QFT. Not terribly many, but they do exist. And they are actually not that exotic. So the first would be where sigma 1 is I1 singularity. So we have, in particular, somewhere here an enhancement from I1 times I1 to I2. And this is a non-resolvable conifold. Conifold Q factorial. So it's not resolvable. And this model has in fact been studied in detail by Braun, Colinucci, Malandro, I think in 2013. And it is also the behavior of the Jacobians of genus 1 vibrations without a section. So the other Braun, Volker Braun and Morrison, 2014, and then subsequent papers. Many more papers have studied this behavior. So this is actually quite often that it happens, at least locally, whenever we look at these genus 1 vibrations without a section that correspond to discrete symmetry groups and look at the corresponding Weierstrass model, it always has these singularities. And just to show you the classification, just if we take type 2, we can also do that. That would be the second model in this list. Then we have at some stage an enhancement type 1, type 2, I1, I2 to type 3. That the details are only for those who are into this classification. This is a hypersurface of the form like this, I equal 1 up to 3 xi squared equals 0. Kleinian singularity, also Q factorial terminal. And there's one more. And that's interesting because it shows what can in general happen. For example, if we take an SPK gauge group, then at some stage we will have likewise an enhancement beyond what is resolvable. So that's the third example. If we take sigma 1 to be an I 2k plus 1 non-split for the X, so that means the gauge group G would be SK instead of SU 2n plus 1 or SU 2k plus 1. Then we have an enhancement point to I 2k. And this again, so this one now, we can resolve, we can partially resolve, we can resolve the gauge group here. But when we do this, we are still encountering a conifold after the resolution. So we can have a partial resolution, but there remains a conifold at this point after partial resolution. So the question is, of course, do we have matter here? What type of matter do we have? And this is now where the matter comes in and why this is important. Because usually we would say, here we have the fundamentals, say, of SPK sitting. And there are many more examples that one can tune. These would be kind of these generic, according to this assumption models, but one can have many more. So this is really something that does occur. Okay, so having hopefully convinced ourselves that it's worth thinking about them, let's look at the math and the physics, properties, and the consequences for matter. So what would one do? So one does... Very good, I'll come to this. Anomalies will be solved in the end. But one has to make changes in the usual formulae. That will be the punchline. So, and so we have such a space. We do the partial resolution. We resolve as far as we can. Then we have some singular space remaining. So why is this bad? In principle, it's bad because on a singular space, there are different notions, inequivalent notions of cohomology. So we don't know which cohomology group to take to begin with in order to count matter. And these different notions of cohomology may or may not have the important properties of Poincare duality and of allowing for a Hodge decomposition and Hodge duality, both of which we are used to using all the time. We don't even remember that we use them, but we use them all the time. And this might go wrong on a singular space, so we have to be very careful which properties we still have and which we don't, what changes if we don't have them. So on a singular space, in general, the ordinary, i.e. the simplicial cohomology, the one that we usually use, the ordinary cohomology, defined by simplices, as in general, a priori, not exhibit Poincare duality. So the statement, now I call it threefolds, that hi h6 minus I of xq, there's a rational and an integer version, of course. This statement that we always use may not hold. And second, may in general not exhibit a Hodge decomposition. So B3 can in general not be decomposed into the H30, 2, 1, 1, 2, and 0, 3, such that we have Hodge duality. 1 second. And Hodge duality. Yes? It's really Poincare duality that may yes, yes, and that I'm already. Yeah. Yes, singular cohomology. Yeah. Indeed. Okay. So the main point, and the main point of this upcoming paper with Andrea, is that if we have QFTs, and under, in fact, more general assumptions, Poincare duality does still hold. And that's a non-trivial statement that wasn't in the literature, and that had to be actually proven. So this is with Antonella to come up. If X is Calabi-Yau 3, and some assumption of this is necessary, it doesn't hold for any for arbitrary terminal space, QFTs, Q factorial terminal singularities, then rational Poincare duality, so over the rational called Poincare duality, still holds. And there exists i.e. there exists a non-degenerate intersection pairing such that dimensions add up. It's non-degenerate, that's still true. And it holds under more general assumptions, but we need, for us now, really Calabi-Yau 3 and Q factorial terminal. And the consequence, why is this good news for us? When we have such a singularity, we do our partial resolution, and then we can proceed as always, even though we have the singularity. So we can, in particular, still compute the gauge algebra by looking at the intersections, the non-degenerate intersection pairing between the resolution divisors and the structure of curves in codimension 1. And likewise, we can compute the matter the way we always do. So if we perform a partial Krapin resolution, so that X has only those QFTs in the end, then the relation between first the usual relations that we all know, the codimension 1 fibers and the non-abelian Lie algebra, and also the relation between the codimension 2 fibers and the matter representation, at least the localized ones. Of course, there's also bulk matter, but that is somewhat also encoded in there. The matter representations, then this relation is unchanged. And again, the reason is that one can consider the usual pairing between the resolution divisors and the curves then in the fiber, compute weights, etc. And all of this works as usual. Say again? Probably yes, we don't know yet. So, yeah. Probably yes, I would say, at least in the ones in codimension 2. There are in fourfolds, there are also those in codimension 3. These are of different structure, but assume that in codimension 2, the end result should still hold, but we don't have any theorems on that yet. Yeah. Yes, so indeed, it has only to be so one possible assumption would be Calabi-Yau and Q factorial terminal, or in fact it's sufficient to have Gorenstein, KLT, and H20 equals 0. Then this result holds. So it doesn't need elliptic, but it has, the H20 has to vanish because between H2 and H4 there might be trouble. That's how it comes about in the proof. But for Calabi-Yau, that's fine. Yes. 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 Both. Both. Everything works as usual, as far as this is concerned.
Is there a physical breakdown at the surface or the
Yes. And to this I come now. So because so far you think, okay, boring, don't. What are you talking about? So, but it's good to know. It's good to know that it works. It's good to know that it works. But now comes what's the actual gist. Namely, what does, yes? We don't know if it's true over Z. So it might be true over Z. It's for sure true over Q. That's also what we need for those applications. Torsion we haven't looked at. Might be, might not. I don't know. So it is still not true. So a Hodge decomposition with Hodge duality, so that if, for example, H21 and H12 are the same, is still not correct. So in general, so there is no possibility to cure that problem. In general, if we do a Hodge decomposition, let me write it in this way, H21 is not H12. So that means there exists no pure Hodge structure and Hodge duality on the cohomologies. This is still not true. In particular, for all those conifolds, it's not true. For the conifold in particular, it's not true. But why would we need this? Because we know that H21 is what typically counts the complex structure of the manifold, and hence hypermultiplets, anomalies, all of these questions have to be addressed now. What one can still do, one can still define and correctly count the complex structure moduli as follows. Namely, when one has Calabi-Yau and Q, again not elliptic, but Calabi-Yau and Q factorial terminal, then by a theorem in the literature, I think it was Kawamata-Steenbridge, I think, there exists a smoothing xt of the singular x, the following properties. So for this complex structure deformations of x are by definition the complex structure deformations of xt, because this is just going to another point in the moduli space. So the complex deformation of x equals the complex deformation. Now, this is a smooth space, so there we count as usual. This is 1/2 B3 of x minus 1. So this is just H21. There everything works out as always. And now there is a second well-known fact how to relate B3 of x and B3 of xt. Sorry, this is xt on the smooth. And the relation B3 of xt is B3 of x plus, and now from singular point P, Q factorial terminal, I get a contribution from the Milnor number, which is essentially defined if you do a smoothing, then you essentially introduce spheres around that point, and that is essentially the number of those spheres. So divided by 2. Where MP, that's the Milnor number of the singular points. And there is a clear way, if you ever encounter this, and you can look this up, of course, compute it. If we have a hypersurface singularity at f equals 0, then MP is given by f coordinates xi, local coordinates equals 0. Then this is the dimension of the coordinate ring over df dxi equals 0. So for example, for the conifold, this would be 1. And for a Kleinian singularity, this can also likewise be computed. So this in particular shows that in general, if this is an odd number, B3 of x is not in agreement with the fact that we have such a pure Hodge structure. So in general, only B3 of x plus sum over p mp is into z. This is in particular true for those non-resolvable conifolds. And this is an odd number. But we can now interpret this equation by telling us now precisely what's going on. Namely, the statement is that at the singular point, we have massless states sitting, which are kind of localized complex structure moduli, which are uncharged under any gauge group, hence do not emit a Coulomb branch, and hence cannot be resolved. So the interpretation is that we can write the complex deformation of x in namely as -1 plus now 1/2 b3x minus, I add and subtract and add mp plus mp. This part is integer, this part is integer. So these are the localized complex structure moduli and these are the unlocalized complex structure moduli. So put differently, these would be the versal deformations of the singularity, deformations of the space, which only change the singularity and nothing away. So the upshot is that at such singular points, one has localized matter, which, however, is uncharged. It's a complex structure modulus, it's a localized one, counted in this way. I'm actually cheating a bit. I can go in more detail if you want. Since it's uncharged, there's no way of giving it a mass along some Coulomb branch, hence there is no Calabi-Yau resolution. That would be the physical interpretation. And now the important question, what about anomalies? That should show up in anomalies in 6D, and it does. It's not in the gauge anomaly. Yes?
How do you know that it's uncharged?
Because if it were, there would be a Coulomb branch. It's uncharged under any, what one call massless gauge group. So there is no Coulomb branch in which direction one would give, in the dual M theory, of course, in the direction of which one would give them a mass, which would correspond to a resolution of the singularity. Exactly, in the dual M, exactly, in the 5-dimensional, absolutely, yes. So these objects do not enter gauge anomalies, and one can check that. One can compute all the charge states in the usual way using this theorem that one can do what one always does, and one finds everything cancels nicely. But what about the gravitational anomaly? The gravitational anomaly, of course, is sensitive to those states. And as you know, from the gravitational anomaly in 6D, namely this relation, one can derive a relation, H are the hypermultiplets, so that includes all the matter, including the moduli. One usually derives from this a relation between the Euler characteristic of the manifold and then the remaining charged matter. And this relation gets modified, and it now looks like this. If you go through it, you get a relation of that type, 30k b squared plus 1/2 k top plus some p mp. That's the new part. This equals the charged hypermultiplets minus the charged dimension of the adjoint of all the groups, plus now again some p mp. These would be, so that's the charged matter, and that's the uncharged matter on the right-hand side, and this is all the rest. So it is here and there that we get differences to the usual formula, and this can again be checked. So that's a new mathematical theorem that can be proven that this holds in fact. Yes, KB is Cartier, because it's Gornstein, so it's a Cartier divisor. That's an integer. Very good, yes. Yes.
In 4 dimensions, maybe not, but in 6 dimensions, there's always some element of K21 after the deformation.
Yes. Exactly. Exactly. So that's precisely this formula here. So after the deformation, we have B3xt, 1/2 B3xt, and that relates the B3 of x and precisely these M of p in that way. The only point is that this is not integer in general. This by itself is not integer. Yeah. 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 Yes. Okay, good. 4 dimensions. So this. So I'm not going to comment on 4 dimensions. It's probably true, which is yes. So well, I think so. In 4 dimensions, there are these terminal singularities in codimension 3. These are something completely different. And then these ones you get in codimension 2. And then my suspicion would be that the same story still works.
But I think sometimes you get these in a non-meaningful way. That is, over certain threefold cases, like we did with Monte Carlo with Weigand, lots of them have these codimension 2 singularities that I think have this flavor, but they can't be deformed.
Good. Very good. So, and that I would say, yes. So, because now the counting becomes more problematic.
There's no
Right. Yes. So one would now so my conjecture would be that now one has to take this the analog of this MP and now does the 0 mode counting properly in 4D, and it might be that the number of those is 0, and then you don't have such a versal deformation. And something which you do not have in 6D. Good. Good. Exactly. If it's, for example, over a P, then you would see that there would be no such 0 mode. But that remains to be, so all the theorems do not yet exist, and if you work with, yeah, so it's not yet clear, but that would be the conjecture. And in fact, it now comes to the second part of the talk, so that would be the goal, understanding how this works systematically, also in 4D, and for this we need to see how matter is counted in 4D, or review first, and then see what's new in 4 dimensions, and that would be the second part. Please. Exactly, absolutely, yes, you're perfectly right. So that's why I said I'm cheating a bit. Really, you should be writing the Tiurina number here. So you would have to. So everything up to here is completely correct. That's what it is. Now in the rewriting, I should be subtracting the Tiurina number and adding it again, and then it would be completely yes. So that here you get the Tiurina number, and here you get everything else, and then these would be the versal ones, and that is then the rest. In all examples that we know of, the Tiurina and the Milnor number are the same. So the Tiurina number equals the Milnor number if this hypersurface singularity is a weighted hypersurface singularity. And all examples known to us are of that type, but we do not know if that is true in general. So I wanted to, for time reasons, put this under the rug, but in principle, yes. In the paper, we do it with the Tiurina number, and then probably I would guess that they are the same in all those examples, but I don't know. Say again, of KB squared? No. Here. Oh, okay. So chi top. This is still age B2 minus B3 essentially, up to, and this second contribution. Those are the Milnor numbers over those points. These are integer numbers. Oh, good, yeah, integer positive. This is integer positive. In here. So because there is this relation that what is it? So it comes from the KB squared. When we have yes, KB squared is 9 minus t. Exactly. Thank you. And then you rewrite it in this way, and you get this 30 from here. So all of this is in the smooth case, this is well known and has been done long ago, and now we just need to keep track of what changes and where changes come in, and this is then the end result. Okay, I wouldn't even have discussed that if you hadn't.
Basic question. When you talk about this smoothing, so did that come, is that a Flavial? Is this some big
Yes.
revolution?
No, it's a complex structure deformation. It's a complex structure deformation. Into a Calabi-Yau.
Oh, I see.
Yes, sorry, yes. So not a blow-up, but a complex structure deformation into a nearby Calabi-Yau in moduli space. And that's infinitesimal, so in particular finite distance. So it exists because it's in particular canonical. So it always exists at finite distance, so in particular infinitesimal. Okay. Good. So, of course, what we are really interested in at the end of the day is in 4D. And I'll now discuss 4D as far as we understand it in smooth situations, and then leaving the rest for future work. So counting charge on elliptic Calabi-Yau 4, in particular smooth. And let me first do some review of particularly well-known stuff. Let me first briefly comment on the local picture, or revise it. This, of course, we remember from the Nagy-Weinhold and from Beasley-Heckman-Waffer. And many more works, Vatari et al., and subsequent work, Sheffer-Namiki et al., and so on, 2008, and following. So, in the local picture, we have the 7-brane along its surface S. That's one component of our discriminant. And then we have another incoming 7-brane, that would be the second part or component of the discriminant. And they intersect over a curve, CR, which is known as the meta curve. It's a curve on the base B3 now. That's the base B3 of the elliptic vibration, where localized matter sits. As in 6D, there are two types of matter, the matter along the brane, and the unlocalized matter and the localized matter. And for brevity, I'm only discussing the localized one. The unlocalized one can be discussed as well. I can give you the details. It's I understood in the same way, but I have to save a bit time. So for brevity, focus on localized matter. And then what is known from the topologically twisted field theory on those 7-branes and worked out in detail is, of course, that we have here matter which come in 4D n equal 1 chiral multiplets. So we have 4D n equal 1 chiral multiplets in representation R, and we have 4D n equal 1 anti-chiral multiplets, again in representation R, and these are counted by the cohomology group by the number of sections of the spin bundle times the gauge bundle. I'll discuss in a second, and these are counted by H1 of this. This comes from the local analysis, where square root KCR is the spin bundle, because the states are independent spinners, spin bundle of CR. It's the spin bundle which is induced by the holomorphic embedding of the curve into B3. Into either S or, more generally, into B3. So you can essentially compute it by pullback in a particular way. There's one that is distinguished, and this seems to be the correct one. We can discuss more later why this might be the correct one. And LR, the vector bundle, or in general the vector bundle, so gauge bundle on the curve, which is induced by the gauge background on S and the other branes. And the question for us, so this is well known, for us is we want to work on a global Calabi-Yau fourfold, and essentially we want to make the connection between this local field theory picture and the elliptic Calabi-Yau. So the question for us would be, first of all, how do we compute the gauge background in terms of the language of the full Calabi-Yau fourfold with gauge background? How do we compute this LI? And how do we evaluate those numbers? How do we compute those cohomology groups? So we'd like to first describe the gauge background globally on the elliptic Calabi-Yau fourfold, and then compute these HI. And I'll be discussing exclusively the smooth case, only smooth Calabi-Yau fourfold for now. In particular, this means I will only be discussing gauge backgrounds which are sort of abelian, because these are the ones that do not obstruct the Coulomb branch in the dual M theory again. So no T-branes as far as this is concerned, and also none of these QFTs for now. That would be the easiest. So let's go step by step in this program. First, the gauge background. So by duality with M theory, the charged matter clearly comes from M2 branes wrapping resolution curves localized in codimension 2. So the charged matter in dual M theory, in the dual M theory picture, M2 branes on fiber curves. On Calabi-Yau fourfold, which are now assumed to be resolved. The resolved Calabi-Yau fourfold smooth. So the picture that we all have in mind is we have here our base B3. We have 7 branes coming in here. For example, a resolved fiber of that type. Here we have a resolved fiber of this type, schematically. And then over here at CR, we have an enhancement of the fiber structure just schematically, because one or several of these P1s, for example this one here, would split into, say, these two P1s. And likewise from here. So now we can look at those P1s which exist only over the matter curve in codimension 2. Say this one here exists, is really trapped at CR. It's only the sum that can be taken away, because it and an M2 brane wrapping this would give rise to a state localized over CR. That's the well-known picture. So in particular, as we know, to each representation R, we associate a weight beta A of R, where A goes from 1 up to the dimension of R. So these are the, say, 10 entries in the antisymmetric of S5, say. To each such weight vector, we associate one state, so an M2 brane, wrapping some linear combination of curves in the fiber, CA in fiber, over CR. So this curve here, for example, I would now call CA for a particular A. So since this curve CA is fibered over the curve CR, this defines the surface. So we define from this, hence, a meta surface SAR fibered over CR CA of that type. And the projection, sorry, I will call pi A, just for later purposes. I'll use it, bring it again when we need it. So that's that's the known global picture of how, or cartoon, how the matter would arise. Now, furthermore, it's clear that the M2 plane, of course, couples to the three-form field of M theory, also well known. So, of course, the coupling is the usual one, C3 over the M2 brane. So the gauge background that will then translate into the gauge background of the branes will somehow be encoded in a gauge background of the three-form. So we have till... Well, okay, good. So the gauge background LR is somehow induced by the gauge background on C3. That's clear. And our aim is to parameterize this gauge background, and we want to parameterize at least two aspects of it, namely first the discrete aspect and then the continuous aspect. The discrete aspect corresponds to what people always call the flux, so that would be the field strength, is the curvature of that gauge background in M theory, which would be a discrete object. But in principle, we'd also like to know about the continuous flat backgrounds, the Wilson lines. So colloquially, and we'll be more precise in a second, we want to understand the field strength, the flux background. This part has studied a lot. We'll discuss that in a second. The background of G4, that would be discrete, but then also the flat or the continuous, potentially even backgrounds or Wilson lines, Wilson loops, and generalizations thereof. That would be C3 along a 3-cycle, which does not necessarily induce curvature. So at least colloquially, this is what we would like. Questions so far? Okay, so this is well-known stuff. And the statement is, that was in the math literature already, or in the math physics literature for quite some while, is that both of this information is encoded in this object known as the Deligne cohomology. So both info is encoded in the Deligne cohomology of the following type. So the Deligne cohomology from the math literature one takes is an object which has the following property. It fits into an exact sequence. There is a map from this Deligne cohomology, which is the actual background, into the space of field strengths. This is H22Z. But it also receives contributions from the flat background, J2 of head Y, so that altogether it fits into this short exact sequence. So that's a property, or you could take it as it's not the definition, but it's a property of that object, and it means the following. So we have here an object, say, AG, a group, an object of this group. And the statement is, this is the full gauge background in the following sense. C2, there exists a map that maps this guy to a field strength, which takes values in H4Z, intersected with H22, which I abbreviate like this. So there exists a surjective map C2, such that C2 of this